Good afternoon and welcome to Calculus in the PM. EJ, I'm your host, Mr. Sindelka. And I would like to put a message from my sponsors first. From Dill Pickle Coca-Cola, it's the taste that refreshes.
I saw you making that.
Enjoy one today.
I'm actually tempted to taste it.
It is, well, sorry, I just finished it.
Is that actually dill pickle though?
Yes, I make it myself. It's fresh squeezed, freshly squozen, if you mispronounce it. But here's differentiability. So derivatives, to do a derivative is to differentiate. So that's the verb, differentiate is to do a derivative. Now, differentiability, can you do the derivative? That's what this is talking about. And after the test, we'll get into some shortcuts too, which is good. Now, the function will not have a derivative at a point P, given by like 2 comma f of 2, where the slopes of the secant lines. Now, this might look confusing, but what is this? This is the slope formula, right? So slope given by the y minus the y, etc., x minus x, fail to approach a limit as x gets closer to a. We've talked about that, we won't go into detail. The next figure illustrates 4 different instances where this occurs. For this example, a function whose graph is otherwise smooth will fail to have a derivative at a point where the graph has 1, a corner. So this is a corner. And it looks like a corner here, the graph here. Now, I didn't trace that very well, but in this particular example, I have the absolute value of x. Now, there's nothing to really do on here, but know that if you have a sharp turn, a corner or something like that, you can't do the derivative. And we even talked about this too before. Why? Because if you come from the left, what does the slope seem to be when you come from the left of 0 here? It seems to be -1. Here it seems to be +1. As you approach 0 from the left and from the right, you get 2 different results. Right? Yeah. Balderdash, you can't have that. Okay, just like a corner, the second thing we call it is a cusp, where the slopes of the secant lines approach infinity from one side and negative infinity from the other. Now that's an extreme case of a corner, really. You can think of them as one and the same. But where would you ever come up with that? Well, x to the 2/3. If you graph this, here's what it looks like. What is x to the 2/3 when you think about it? Just here, incidentally, this function. It's not that crazy a function if you think of this as the cube root of x, and then you square the result. Right? And incidentally, that's what this is. That's 2/3, agreed, right? Mm-hmm. Just in regular notation. If you graph it, it looks like a seagull almost, right? You know how in grade 3, well, look at how my daughter drew seagulls when she was 5 or 6 years old, right? Just the same way. X to the 2/3, right? Okay. And it's the same argument. If you come from the left, you're going to get a different result than if you come from the right. And as a matter of fact, it's going down so low, it's negative or positive infinity. So the derivative doesn't exist at 0 in that case. What else? If I just took the graph of the cube root of x, instead of squaring it before, this function. This is what the function, oh, I thought I still had my magic pen, I don't. Okay. Right here, you can just visually see. If you were to do the slope of the tangent line there, it looks like it's going, the tangent line is straight up and down the y-axis. So if you have a vertical tangent line, that's an infinite slope, either positive or negative infinity from both sides. That means it doesn't exist. Remember, infinity or negative infinity is not a number, but we put it down, it's the same as undefined, but it's more descriptive. So if you could put down positive or negative infinity, you do that because it just describes your undefined value or undefined answer a little better. Question.
It's in the straight, it's not straight, because it's going back down.
Okay, the slope of the tangent line though at 0, you know how if you approach from this side, it would eventually become straight up and down from the left. From the right, it would also become straight up and down. Do you see what I'm saying? So right at 0 it is. Anywhere else though you could do the derivative and it exists. Okay, so if you have a picture like that, and then discontinuity from the left, from the right, you definitely get different values, okay? Actually, in this case, it's full. You might argue, well, from the left, I get 0. From the right, I get 0. But to be differentiable, you have to have a continuous function. If f has a derivative at a point, x equals a, x equals 0, then f must be continuous at that point as well, okay? So going back to this, even though this might even look like from the left and the right, you get the same derivative, it's not really true. And actually, it doesn't even work. No, I say, note. So if you're given a piecewise function and it's not continuous, no dice. Now just take a look at this note here. The left side of the derivative does not exist. The left side derivative here, because of this hole here. The right side derivative of this function ux does exist. Now I'm asking you, why? What is the definition? From the right side it works because, so I'm going to call this the right side derivative. I'll sort of answer the question that's on the right. Pushed off to 0, and we just sort of thought about it as we did this. Yes, Emma?
So all we need to know is that it won't have a derivative if it's not continuous.
If it's not continuous, it won't have a derivative, and as far as one-sided derivatives, it has to include that spot, whichever side does.
Say the dots were reversed, say the bottom one was closed, and that would be a derivative.
Then we could have the left derivative, yes.
Are you going to know all the reasoning, or do you have?
You never, with a test question that I didn't create, I'm not sure, because maybe they could give it to you in some way where you'd have to think about it. That's why I'm sort of saying, the reason why is you can actually do it from the right, you can't do it from the left. But I doubt that you'll have to, but I'm not certain. You'd probably be able to skip that question, honestly. Show the function is not differentiable at 0. Now we'll get into this. Yeah, sometimes, Paul, you're asking good questions, but we were getting into it. Okay. The first thing is, to be differentiable, we assume one thing, it's continuous if it's differentiable. If it's not continuous, then you can stop. Now, I have the picture here, and it looks continuous, and then a straight line. And verify it with the equation. At 0, 0 cubed is 0. If you could put 0 into here, it would also be 0, right? So it's definitely continuous. That's the first thing you check for. It's the easy thing, at 0. So this is continuous, CTS, at x equals 0. Okay? So that's not why it's not differentiable. So let's think something else through. And we can use our know-how if you know a little bit about functions. Let's say the derivative, f prime of 0, but we'll say from the, how about this? I'll put a little green left. This is our notation, we'll say from the left. This is not necessarily universally accepted, that I'm aware of. F prime of 0 from the left is what I'm saying.
Why do you have to put both?
Which one is?
If they're negative and the left.
Well, just to show you what I mean by the little negative sign. 0 approach from the derivative from the left. Just to, I guess. Now, what do you guys know about x cubed? If I had the whole function, it would look like this, wouldn't it? do you guys know enough about the shape to say at 0, what would the tangent line be? Can you kind of just see it? It would be 0, okay? We're not going to work it out. I'm not going to ask you to cube x plus h. Okay? It should be 0 from the left. Now from the right, it's a line.
Are you doing this for x cube only?
Oh, from the left, I did it for x cubed, because that's what's on the graph. But from the right, it's the linear function, 4x. Every point on that line has a slope of 4. If you approach 0 from the left or the right, you should, if it's differentiable, you'll get the same answer. You don't here, do you? This is not differentiable, and it's because the left and the right side limits don't match at 0. So it's non-differentiable at 0. Now that's...
So you're right that left and right derivatives doesn't match?
That's right. We could say the left and right values aren't the same, or... Not the same for the derivative. So we could say, therefore, f prime of 0, either side, doesn't exist. It's not defined or undefined, doesn't exist. Same thing. You could say it a number of different ways. Now, don't always assume that a piecewise function doesn't work at that point, though. And I won't go through it, but can you see if I change the second function to, well, temporarily, instead of 4x, what if this was x squared? And x cubed hitched up to x squared right here. You know how x squared right at 0 would have a 0 tangent line? So there would be an example of a piecewise function where the derivative does exist at every point. Right? So don't just assume piecewise functions at their connections don't exist. That, for derivatives, they could. You have to think about it a little bit. Last thing, I hope you have your calculator too, because we're going to get into that. Now, I put, this seems trivial, but it's important. Trivial means like a little fact, sort of. But, well, I'm going to read from my paper. My eyes aren't good when I read from the board. A good way to think, just skip up to here quickly so you don't miss this. We can do it after. Good way to think of differentiable functions is that they're locally linear. That is, a function that is differentiable at a, that number that you're testing, closely resembles its own tangent line, very close to that number a. Now, many graphing calculators, etc., use these points. I'm going to pause this because if you're at home doing this, you can read